Do you know what time it is? Time for more calculus. I feel like I've asked that a couple times each time that I've been doing this, but I could ask, do you know what time astronauts eat lunch? Lunchtime. Okay, it's time to do calculus. So here we're going to talk about the relationship between continuity and differentiability. So we're going to walk away from rules about how to differentiate functions, so like the product rule, the quotient rule, the chain rule, wow, for a couple days. And we're going to go to, well, maybe not a couple days, but for right now we will, the relationship between continuity and differentiability. So before we even do any more on this, I want to remind you what a continuous function, what is the three-part definition of continuity? The function has to be defined. The limit from the left has to equal the limit from the right, and the function value has to equal the limit. Great. Okay, so that is good to keep in mind, but also just with continuous, that if you're going through a function when you're looking at it, and you would never pick up your pencil at all. So if you were tracing it from the left to the right, you never pick it up. You would be able to go, and it can be jagged or whatever, that's fine, but you never pick it up. So here we're going to consider this function. So we have this function, square root of x squared minus 4 at x equals 2. So what I want to know is this function continuous? So I'm going to go over here and I'm going to actually graph this. At x equals -2, I would get 0. And you could take a calculator, by the way, and do this. You could say, well, y equals, and then you could, in y1, do the square root of x squared minus 4. And then from there, go to a table. Oh, I have a weird table setting going on right now. I'm going to start at 0, and I'm going to go up by just ones. And I can see I've got some errors in here. That's okay. That just means that at those values, the function is not defined. But I can see at -2, I get 0. And -3, I have 2.3, so somewhere around there. -4. 3.4. So that's about enough for me to see. On the other side, I've got 2, 0 is right here. 4, 3.4. It's way up here. 3 was 2.3, so I'll go there. I like this. So this particular, ooh, that was kind of off. This particular function, and I'm going to label this f of x, looks like this. Okay, so if I'm just looking, is this function f of x continuous at x equals 2? Not so much. I can see if I go a little bit to the left, the limit doesn't exist at all. So it just doesn't work. So what I'm going to do is I'm going to say no. And my justification now has to be based on that three-part definition. So if I say f of 2, the function is defined, I get 0. But the next thing I check is, does the limit exist? The limit is x approaches 2 from the left of f of x. Does that equal the limit as x approaches 2 from the right? The limit as x approaches 2 from the left, it doesn't even exist. There's nothing down here, so it does not exist. Obviously, that can't be anything from the right, which would just be 0, but this doesn't make sense. So I'm going to say as limit as x approaches 2, f of x does not exist. F of x is not continuous at x equals 2. For right now, how we're going to do differentiability is I'm just going to find the derivative. So I actually do get to use some derivative rules. It's like a fancy surprise. Or a fun surprise. Maybe not fancy. It's not like we're dressed up for this. But if f of x is square root of x squared minus 4, I'm going to say that this is x squared minus 4, so the 1/2 power. If I take the derivative, you could also argue, by the way, that this graph, because the square root was already there, that we wouldn't also need the negative square root. But if, because we didn't introduce the square root. So if you just argued that this part of the function was the only part, that would be okay too. The derivative, you take the derivative of the outside because this is the chain rule. Wow. Leave the inside alone. Times the derivative of the inside, which would be 2x. If I simplified that, I would get x over. In the denominator, I would have x squared minus 4 to the 1/2, which is the same thing as x over the square root of x squared minus 4. If I try substituting in f prime of 2, I would get 2 over 2 squared minus 4. I suddenly can't even say those are equal anymore because this would just be 2 over 0, which does not exist. So all I'm going to say is f prime of 2 does not exist. Find the value of f prime of 2. It does not exist. To determine if this is differentiable, we're going to say big fat no. And I was angry about it, so I put an exclamation point. Let's do it. So the first one didn't work out so well because we saw the function wasn't continuous, nor was it differentiable. So let's try another one. Let's see if this one might be. We've got consider this function f of x is equal to x cubed plus 2, or x to the 1/3 plus 2, so sorry, at x equals 0. So to plot this, I'm going to say this is y1, and I'm going to say x to the 1/3 plus 2. Go to my table. And I can see at, oh, I've got lots of values. At 0, 2, it's one of those. At 1, 3, 1, 3, got another one. I'm just going to get a few more. 2, 3.2, so around there. At x equals negative 1, 1. And let me do another one. X equals negative 2 is 0.74, so around here. And so I know that it's going to look something like this, so that's enough for me. That was a pretty good function, so just saying. Based on the graph, is f of x continuous at x equals 0? Well, if I look right here, it sure looks like it's continuous to me. I don't have to pick up my pencil, so I would say yes. But in order to explain my reasoning, I have to use the 3-part definition of continuity. And that is, the function must be defined. F of 0 is 2. The limit has to exist. For a limit to exist, the left has to equal the right. So the limit as x approaches 0 from the left must equal the limit as x approaches 0 from the right of f of x. And in this case, from the left and the right, I can see I'm approaching 2 from the left, 2 from the right, 2 equals 2. So the limit exists. And then I'm going to say the function value equals the limit, which in this case is 2 is equal to 2. So I would say yes, we got it. Now I want to find f prime of 0. So f prime, I would have to find f prime of x. So using the power rule, take 1/3 x, subtract 1 from the exponent, I would get negative 2/3. The derivative of 2 is just 0. I'm going to rewrite this as 1 over 3 x to the 2/3. Oh no. And then I try to substitute in 0. 1 over 3 times 0 to the 2/3. And I don't even want to put equals anymore because this would just be 1 over 0. No, because f prime of 0 does not exist. Okay, let's do another one. Let's just see. We consider this function. This one is x to the 2/3 plus 2. So change this slightly. If I go to the table, and you could also graph this, just push graph to make sure that you've got the right thing going on here. But x to the 2/3 plus 2. If I find some values in here at 0, 2, that's 1 point. Another point on my graph is at 1, 3. Another one is at 2, 3.5. And this one's at negative 1, 3. What's another one? Negative 2, 3.5. Negative 3 is 4 point something. I don't even need that one. So it's drawn like this. Hey, that's exactly how I draw birds on a paper too. I'm a really great artist. No, but that is how I draw birds, like far away if you were in elementary school and you're like, ah, I drew a bird. Kind of looks like my bird. Based on the graph, is f of x continuous at x equals 0? I don't pick my pencil up, it looks like it. This is a marker. But, so I'm going to say yes right away because I can see that it's continuous. There's no holes, there's no vertical asymptotes. But the next thing I need to do is actually use the three-part definition of continuity, which means the function is defined. F of 0 is 2. I need to see, does the limit exist? So the limit as x approaches 0 from the left. Does that equal the limit as x approaches 0 from the right? Yes, from the left and right, I get 2, which equals 2. And does the function value equal the limit? Yes. Limit as x approaches 2 of f of x equals f of 0 because both of these are 2. Woo, we proved that. Now I find f prime of 0. Maybe this will be the one. Maybe this will be, you're saying, you're kind of hoping. Please, please, please let the derivative exist. Let's try it. F prime of x, we're using the power rule, which would be 2/3 x. Subtract 1. So 2/3 minus 3/3 would be negative 1/3. The derivative of 2 is 0. Oh no. F prime of 0 would be 2 over 3 times 0 to the 1/3. Oh no. I don't even want to put equals because now this was 2 over 0, which is not a thing. So f prime of 0 does not exist, which means no. So sad. So we did all this work, and so even in cases where the function was continuous, it doesn't necessarily mean that the function is going to be differentiable. Don't worry, we're going to get to some very quickly that are differentiable. Apparently, my very quickly is not super fast though. So based on what we've seen, does continuity imply differentiability? So if a function is continuous, does that mean that continuity implies differentiability? No. Continuity. So just because a function is continuous does not mean it's differentiable. Differentiability. This last part, I'm going to tell you, even though from the previous examples you wouldn't have been able to tell, but differentiability does imply, or I'm going to just say it implies continuity. Meaning if I know a function is differentiable, it is going to be continuous. So if a function is differentiable, it's also continuous. We'll say this a bunch of times, but for right now, all that you've really observed is that continuity does not imply differentiability, because you just saw several examples where functions were not continuous, or were continuous, I'm sorry, and were also not differentiable. So it's not like because it was continuous, it had to be. It's not the case. Although if a function is differentiable, it will be continuous. So this is kind of the new thing, you know, like if a limit exists, then the left has to equal the right, or if the function value is, if the function is continuous, then the function value exists. The limit exists, and the function value equals the limit. This is another one of those things that you really need to know. In order for a function to be differentiable at a point x, the function must be continuous. You can't take a derivative of something that's not there. The other thing is, the slopes must be approaching the same values from the left and right. Same value from the left and right. And if you're thinking, isn't that just limits? Yes. But what this is the limit as x approaches, let's say a, if this is at x equals a. There we go. Limit as x approaches a from the left of the slope, which would be f prime of x. I'm going to say this function f of x. So this function f of x. So then I can write this notation. The limit as x approaches a from the left of f prime of x has to equal the limit as x approaches a from the right And so let me give you an example of what that is. So if you have a function that has a nice smooth curve, it's going up, it's going down, you know, like it's nice. Even at this place right here, the derivative at that location would be 0. And the reason why is because this original function, f of x, has a horizontal tangent there. But if I would go slightly to the left at this point, it's going to be like there's still a slope here, here. So it like gradually goes. So as you get to the top, it smooths out and then moves over. Whereas if I had a function that looked like that, there we go. It looked like I had a hat on or something. Hold on, let me do it. There we go. It's like a hat. Okay. If I am like this when it's just me by myself, just making notes, just get ready for if I, you know, if and when in class I ever instruct you on something, it's going to be awesome. Okay, so in here, the slope of this line, let's say this is a slope of like 1. And then drastically it changes to -1. These slopes are not approaching the same value from the left and the right. It's not like it smooths out and is nice. So this part, the slopes must be approaching the same value from the left and the right. This means no sharp turns. It also means that you can't have something, where was one like that? Like this is considered a sharp turn. You see how it's kind of, sometimes it's called a cusp. It's quickly changing. This one, what actually is happening is it becomes a vertical asymptote. My drawing just isn't that awesome. Like it could be over here and then there again, but there's actually going to be a vertical asymptote. Those ones are a little bit harder to see, so you wouldn't just have a graph normally to like be able to observe those. Okay, let's just keep going now. This one says, consider this function, g of x, and it says, is g of x continuous at x equals 3? So this you've done before. You could have done this long before this day. Is this function continuous? Well, let's use the 3-part definition. Is the function defined? G of 3. I can see up here this is as less than or equal to 3, which means that I use that top function. And I want to write this out like the square root of 3 plus 1, so anybody reading this, including me, I would be able to know which part of the function you're getting this from. Square root of 4 is 2. So we're good. The next thing we need to do is the limit as x approaches 3 from the left of g of x. Is that equal to the limit as x approaches 3 from the right? So does the limit exist? 3 from the left would be this part of the function. So I wouldn't have to do this again because I already did it, but I'm just going to say that, square root of 3 plus 1. And again, I didn't have to put plus or minus 2 here because I didn't introduce the square root. On the right, limit as x approaches 3 from the right of g of x would be 5 minus 3, because I'm substituting the x. I get 2 is equal to 2. Yay! So right now I can see that the function value exists. The limit exists, and I can see the function value equals the limit, because they both equal 2. And so I'm going to say yes. And I showed my complete analysis. I'm good. So is this function differentiable? Well, the first thing it says show a complete analysis. For a function to be differentiable, it must first be continuous. And I can say g of x is continuous at x equals 3. And I'm just going to say see above. So I don't have to write all that business again. But it's really important on the AP exam, on tests, that if you use something from a different section, so if this is part of your analysis and you want to use it, that's fine, you don't have to write it again. But you have to write C part A or C above, like C whichever thing it is. If it's in part A, you would say C part A. Because if not, AP readers, the people that are going to be reading your AP exams, are trained to only look in the box that the question is in. So there'll be a box and you'll have to respond in there, and then that's it. They can't go back to other parts unless you have indicated to do so, and then they can. So g of x is continuous at x equals 3. And then the next thing is the slopes. Are they approaching the same from the left and the right? So is this true? It's weird because I only put part of a box. So limit as x approaches a from the left of f prime of x, or in this case g prime of x. And I don't even have to just say a, I can say 3 from the left, equals the limit as x approaches 3 from the right of g prime of x. And g prime of x, you might be saying, I don't have that. All I have up here is g of x. Well, you can make it. So you're going to write g prime of x. You're going to make your own little thing over here. X plus 1, the square root of x plus 1 is the same thing as x plus 1 to the 1/2. If I took the derivative, I'm just doing on this on the side, 1/2 x plus 1. My new exponent is negative 1/2. Wow. So if I rewrote this down here, I would get 1 over 2 square root of x plus 1, because I rewrote this business. It's still going to be on the same interval from 0 to 3. 5 minus x. The derivative of 5 minus x is negative 1. And this is still from 3 to 5. And now I can set these up. So I can say the derivative of 3 from, or the limit as x approaches 3 from the left of g prime, substitute in 3. So I get 1 over 2, 3 plus 1. And is that equal to negative 1? It's not looking good. 1 over 2 times 2 is 1/4, which is not equal to negative 1. So we're going to say, sadly, no. And my complete analysis is this. I showed that it was continuous, which is good. And then the next thing I did is I tried to see, is the limit from the left equal to the limit from the right? Let's do one more. Sorry, that's a weird squeaking sound from my chair. Oh, these ones are fun. Is that scary if I say that they're fun? Okay, if you need to stand up and take a stretch break, now would be a good time so then you can think and focus. For what values of k and m will the function be both continuous and differentiable? Okay, so for a function to be continuous, remember the function has to be defined, which if we're talking about x equals 3, it is. Because I can see right here, I can substitute in 3 into here and I'm good. So it's not asking me to show my incomplete analysis. It's just asking me to find the values of k and m, showing my complete analysis. So I'm like, okay, I'm good. I know the function is defined. That's good. And I can see that if it's defined, it's also going to be the limit as x approaches 3 from the left is going to be whatever this is. So as long as these two things are matching, meaning the limit as x approaches 3 from the left of h of x has to be equal to the limit as x approaches 3 from the right. From the left, that's going to be also the function value because that's where it's less than or equal to 3. So I know eventually, after I get these two things equal, it will be equal to the function value. So if I do just this part, I'm going to say k, the square root of x plus 1. I'm going to substitute in x is 3. On the right, I've got mx plus 2. So instead of x, it says m times x plus 2. Instead of x, I'm going to put in 3. Now I've got square root of 4, which is 2. I didn't introduce it, so it can just be positive. So 2k is equal to 3m plus 2. And you might be thinking, okay, great, I can't really do anything with that. I could divide and say k is equal to 3/2 m plus 2, or plus 1, but that wouldn't be good enough because I need to find the values. So this was continuous and differentiable. Well, to be differentiable, what has to be true? The function has to be continuous, x equals 3, and the limit from the left of the slope has to be equal to the limit from the right of this slope. Slopes have to be approaching the same value. So I'm going to say the limit as x approaches 3 from the left of h prime. And you really have to make sure that you're writing this down. A lot of times we'll say justify your answer using limits. This is what you're doing. You're writing this down. And you might say, I don't have h prime, but you can find it. This would be k is just a coefficient. And I think I should be more clear because this happened not very long ago where you had k as a coefficient, but k is just a coefficient. So you can take this along for the ride. This would be like k x plus 1 to the 1/2. So if I take the derivative, that would be 1/2 k. There's no product rule needed because k is just a coefficient. X plus 1 to the negative 1/2. Wow, times the derivative of the inside is just 1. So up here, I'm going to say that this would be k over 2 square root of x plus 1 from 0 to 3. And then mx plus 2. The derivative of mx plus 2. Really, this looks like mx plus b. The slope is just m. because again, this is just m and k in this case. They are just numbers. They are just coefficients, so we're treating them like that. So now when I say the limit from the left and the right, I can say k over 2 square root of 3 plus 1 equals h prime. I would just get m k over, this would be 2 times 2, which would be 4. K is equal to 4m, which means, were you thinking you were really hoping to do systems of equations today, and you were hoping anytime you saw a k to substitute in 4m instead? Oh, we are on easy street now. I've got 5m is equal to 2. And then divide both sides by 5, which means m is equal to 2/5, which would mean k is 4 times 2/5, also known as 8/5. Ta-da! We did it! Well, we did that one. We have one more to do. And by the way, you can check this by substituting in k and m and then trying these things again, substituting in 3. Does that work from the left and the right? These are not nice numbers many of the time. The next ones are not nice either. So substitute in back into k and m, and then you can actually just see, does this work? If I take the derivative, is the left equal to the right for the function itself, substituting in 3? Is the slope, the derivative, equal from the left and the right? So do those limits exist? This one, what are the values of a and b that will make the function below differentiable? This one didn't give me continuous, but if a function is differentiable, it's also continuous, which means I still need to be thinking about limit as x approaches 1 from the left of f of x being equal to the limit as x approaches 1 from the right of f of x. And I need to think about, because this is differentiable, 1 from the left of f prime being equal to the limit as x approaches 1 from the right of f prime. And again, because I can see x is less than or equal to 1, the function is going to be defined, and it will be equal to whatever the limit is from the left over here. So I don't have to worry about showing that part. The next thing I do is the left and the right. So this says 3, and a and b are both considered coefficients here, so I can just take it along for the ride. When I have the value of x, though, I need to substitute in 1. So 3 times 1 squared plus 2 times b times 1 plus 1. From the right, a times 1 to the 4th minus 4b 1 squared. Oh no, I'm going to run out of room. Minus 3 times 1. There we go. I put up a barrier. You never even knew that I went that far. This would be 3a plus 2b plus 1 is equal to a minus 4b minus 3. And then I don't really need to do something else with this, but I'm just going to make it a little bit nicer. So I'm going to subtract a on both sides. I get 2a. I'll even put this on the same side. It doesn't matter. So I'm going to subtract a on both sides. I'm going to add 4b on both sides. And I'll subtract this 1 on both sides. Good enough. And if I see this, I'm like, hey, all these things are divisible by 2. I could say a plus 3b is equal to negative 2. And then I'm going to stop there because I need to use this other function. So over here, I'm going to say f prime of x. This would be 3ax squared. Remember, a is just a coefficient. So 2 times 3 is 6. There's a tractor outside. 6ax. Now that would be to the first power. So that's good enough. This one would just be plus 2b. And this is where people always mess up. Don't let this be you. Don't volunteer as tribute. The derivative of 1 is just 0. A lot of people, when they're doing this problem, because there's so much involved in it, they just write down 1. Don't let that be you. Down here, I've got 4ax to the third minus 8bx minus 3. And again, this is x is less than or equal to 1. This would be x is greater than 1. So the limit from the left would be 6a, and then you're substituting in 1 plus 2b. From the right, 4a, 1 to the third would just be 1 to the third minus 8b times 1 minus 3. So I've got 6a plus 2b, 4a minus 8b minus 3. I'm just going to put these together a little bit, subtract. So I get 2a plus 10b is equal to negative 3. Okay, and then from here, you know what? I'm not even going to use this one anymore, because do you remember another way to solve a system of equations? If you remember way back to Algebra 1, you can solve a system of equations by using linear combination where you add up the columns. But in order to do so, I'm going to multiply this bottom row by -1, that means negative, negative, positive, add up the columns. This would go away. I would get negative 4b is equal to negative 4 plus 3 is negative 1. B is equal to 1/4. So I found B. And then to find A, maybe I will use this. A plus 3b equals negative 2. A plus 3 times 1/4 would be 3/4 is equal to negative 2. Oh man, this is where it can get confusing. Negative 2 minus 3/4. Negative 2 would be like, put this over here. Negative 8/4 would be negative 2 minus 3/4 would be negative 11/4. And this is one, if I got this answer in a test, I might be like, I'm going to go up here, substitute some things in, sub in 1 from the left and the right and see if I'm right. But I can see, because I've done these notes before, that I can just compare it with that. And we did it! Whew, that was a big one. Thanks for sticking with me. I think you're great. Seriously, I can't sing your praises enough. Thanks for letting me teach you. Bye. Let me know if you have any questions. Bye.